We will consider for the reactions of the conjugated system, the reaction first with HX, and then we're going to consider the reaction with the halogen. I just want to point out the difference between an alkene reacting with HX and a conjugated system reacting with HX. So just to refresh your memory in there, when we were talking about alkenes, and we reacted alkenes with HCl, let's say, for example. We said that the reaction followed Markov-Nikov. It followed Markov-Nikov because, let's say, if I have a CH3 over here, because you want to form the most stable carbocation. So hydrogen, because you start adding your hydrogen first, your double bond is always your nucleophile. This is the source of electron, and this is where you need to start your reaction. So your nucleophile is going to open up and grab the hydrogen because the hydrogen is partial positive. And here you're having a reaction between a nucleophile and an electrophile in there. And then the chlorine is going to leave. So the first thing that you're adding here is the hydrogen. Hydrogen goes to the less substituted carbon because you want your most substituted carbon to be a carbocation. So hydrogen adds, in this case, to the less substituted carbon, and your plus charge is going to be on the most substituted carbon, and then your chlorine is going to come and attack your plus charge in there, and you're going to end up having your product. So at the end, I would add my chlorine to the most substituted carbon. This here is Markov-Nikov. Markov-Nikov is a rule that is put in order to get the most stable carbocation. And we're going to keep working with Markov-Nikov. So with Markov-Nikov, the hydrogen is not necessarily adding to the less substituted carbon, but it's always adding to the less substituted carbon whenever you have a system of one double bond. But if you have a system of two double bonds, the hydrogen is not necessarily adding to the less substituted carbon. So I would go by the definition of Markov-Nikov to form the most stable carbocation. This is going to be our target, okay? Because there's a difference between a system of one double bond and a conjugated system. So let's have an example. Let's start with a simple one. So if we have a conjugated diene, this is a symmetrical conjugated diene. So this is a symmetrical conjugated diene. It is symmetrical because both double bonds, they are connected to the same group, so they are going to be the same. So it doesn't matter if you start your addition from this carbon or you start your addition from this carbon. Let's go ahead and react this with HCl. See the difference. We said that we have 4 p orbitals in there, and each p orbital has 1 electron. The thing about dienes is that, or conjugated dienes, is that you cannot break one double bond without breaking the other. So let's go ahead and see. It's always in these reactions, we're going to follow the rule of nucleophile. So you're always going to pick your nucleophile and you're going to pick your electrophile. The nucleophile is the source of electron, and in this case, it's going to be the double bond. The electrophile is going to be the hydrogen that is connected to the chlorine. Why it's a positive charge? Because chlorine is an electronegative element. As we always explain, chlorine is going to pull electrons away from the hydrogen and make it partial positive. So now you're going to have your electrophile here, your nucleophile there. You can start the reaction. The reaction always starts from the nucleophile towards the electrophile. So my first step here is the addition of the hydrogen. So you go ahead and you add your hydrogen in there. Now, the idea is I want to form the most stable carbocation. So in this case, I'm forcing my hydrogen to go on this carbon because I want my plus charge to be here so that it's going to be allelic to the double bond. I don't want my plus charge to be on this carbon. So this is why, because if it is on this carbon and I added the hydrogen here, the plus charge will be far away from the double bond and will not be allylic. And my target is to get an allylic carbocation. This is my target in there. So what I formed over here is a secondary allylic carbocation. Okay? Now, as I said, whenever you are working with conjugated systems, you cannot form an allylic carbocation without doing resonance. So you cannot break, because I broke one double bond in here. You cannot break one double bond without breaking the other. Those two are connected in there. So the moment you go ahead and you form your allylic carbocation, you need to do resonance immediately in there. And when we do resonance, then the double bond, we start our resonance from the double bond. So from the double bond towards the plus a charge in there. Why? Because the double bond is the source of electron. So from the more electron to the less electron. The less electron is the plus a charge in here. So now my new positive charge is going to be on this carbon over here, and my new double bond is going to be between carbons 2 and 3. Let's go ahead and number the carbons. So I'm starting with 1, 2, 3, and 4. This is 1, keep the same numbering, 3 and 4, and this is 1, 2, 3, and 4. See the difference in there? Your double bond here is between 2 and 3 in the second resonance form. Here your double bond is between carbons 3 and 4. Now I produced two different carbocations in there. This is a secondary allylic, and this one is a primary allylic. Both are going to form. Both are going to be stable. Both are going to form. But of course, the secondary allylic is slightly more stable than the primary allylic, but both are going to form and lead to a product. The type of product that we are seeking is solely depending on the temperature of the reaction. So let's go ahead and write all the products and then look at the temperature of the reaction. Now here I have a chlorine in the solution because chlorine left after the double bond took the hydrogen. Every time you make a bond, you break a bond. So when chlorine leaves, it's going to be in the solution. So now chlorine is going to come and attack every single cation. So you're going to have a Cl minus here attacking, and you're going to have a Cl minus in there attacking. Remember that carbocations are planar. And you have to consider stereochemistry if you are creating a chiral center. So over here, I do have a potential chiral center on this carbocation because it has 3 different groups around it, and I am introducing a chlorine in there, which is a 4th one. So when the chlorine is going to attack, the chlorine is going to attack either from the top, or it's going to come and attack from the back. So you need to show stereochemistry in there that you are forming 2 products. So the chlorine is going to be in front, plus that is going to push the hydrogen at the back, plus the chlorine is going to be at the back. That is going to push the hydrogen in front. These two are pair of enantiomers in there, okay? And these two, we need to give them a name for the product. It is a 1-2 addition product. Why? Because I added the hydrogen on carbon number 1, and then I added the chlorine on carbon number 2. So this is going to give me the 1-2 addition. It's called an addition because you add to the double bond. All reactions involving alkenes, they are addition reactions because you're adding to the double bond. You're breaking the pi bond and you're adding 2 sigma bonds. This is the opposite of elimination. So this is called a 1-2 addition reaction. And we're going to call this a kinetic product. Kinetic products are very fast product. So this is a very fast product. The reason why it's very fast, because of the close proximity of the chlorine to the carbocation. It's very close to the carbocation in there. The carbocation is not far away. So this is why the first thing that happens here is the 1,2 addition. Kinetic products, they happen at a low temperature. Normally it's less than room temperature. In there. So let's assume if your room temperature is 25, then if your temperature is less than 25 degrees Celsius, then in this case, you're going to end up having a kinetic product. Kinetic products, they range their temperature from 24, 23, they can go to 0, or they can go to negative 70. So any temperature that you see below 25 degrees Celsius in there, whether it's a 0 degrees, whether it's a negative 15, negative 70 degrees in there, whether it is a 24 degrees. So all of those are considered to be less than room temperature, and those are going to favor the kinetic product. The kinetic product is the 1,2 addition product, and that is going to be your major product in there. So that is going to be your major product at low temperature. So it all depends on the condition of the reaction. What are the conditions of the reaction here? You're going to read the condition of the reaction underneath the arrow. If it says low temperature, then you're going to do the 1,2 product in there, and that was going to be the major product. Now, if it says a high temperature is going to favor the 1,4 addition. So here you have the 1,2 addition, and then the other chlorine, since I am not creating now here any chiral center in there, because the plus charge is a primary, then the chlorine is going to come and attack over here. I have 4 carbons, and I need to keep having 4 carbons in there. I am adding to this carbon a chlorine. Okay, and let's go ahead and do the numbering in there. Now see my position of the new double bond. Now it's between carbons 2 and 3, and this is how always the 1,4 addition needs to look like. The double bond needs to be between carbons 2 and 3 of the conjugated system. And here I am only numbering the conjugated system in there. So let's say if you have a bigger chain of a lot of carbons on the sides of the conjugated system, just ignore and only number the conjugated part of the molecule. So here I am ending up adding 1,4 addition. 1 on 1 you have the hydrogen, and on 4 you have the chlorine. So this is called a 1,4 addition. 1,4 addition is normally the thermodynamic product. Now, the thermodynamic product takes more time in order to form. The reason why, because the chlorine is far away from the plus charge. And when it forms, the most stable alkene needs to form. Here, this is a disubstituted alkene, versus here it's a monosubstituted alkene. So the more substituted alkene is going to form in the thermodynamic product. The thermodynamic product happens at a high temperature. And the way that we're going to measure our high temperature is going to be more than the room temperature. So let's say, for example, if you have 26 degrees and above, then in this case, your product, your major product is going to be the thermodynamic product. So that's going to be the major product at high temperature. So if you go up there and you read underneath your arrow, let's say 40 degrees Celsius, then in this case, you don't have to mention the 1,2 addition. This is going to be the major. What I would do is I would list all the products and then circle the 1,4 addition, and that is going to be my major product in there. This is an example for a symmetrical conjugated diene. Let's go ahead and do unsymmetrical conjugated diene example. As I said, our target is to form the most stable um, carbocation. And the most stable carbocation is an allylic carbocation. This is always the case. So let's go ahead and react this, for example, with HBr. And here I want you to put all possible products. Okay, products. And I'm going to be really clear what I want you to do in there. So when you see like room temperature or all possible products, just go ahead and write both products, the 1,2 edition and the 1,4 edition in there. Now this is an unsymmetrical diene. You can easily see that this double bond is different than this double bond in there. The connections are different. Everything is different. This double bond has a CH3 on this carbon and the CH2 on this one, and it's connected to a carbon with a CH3. This double bond has a carbon that is connected to a CH2 and another CH2. So see the difference in there? So this is an unsymmetrical alkene. So the question is here, from which end would I start? You have two ends. You have here an end, and you have here an end. So which end are you going to start? Well, we're going to start with each one separate. And then we're going to look for the most stable carbocation. So we're going to look for the end that gives us the most stable carbocation when we are doing our mechanism. And whenever we get the most stable carbocation, it's this path that we need to go with. Okay, so let's go ahead and start with this carbon over here. Okay, I'm gonna go ahead and highlight my conjugated system because my addition is gonna be on my conjugated system. So my conjugated system is this double bond, the sigma bond, and this double bond. So this is gonna be my conjugated system over here. Okay, so I'm gonna start by numbering this as 1, 2, 3, and 4. So I need to end up getting my products, my 1,2 edition and my 1,4 edition every single time I add. Now, in this case, again, you need to add according to Markovnikov. Markovnikov in conjugated systems does not mean hydrogen adds to the list substitute of carbon. Please pay attention. Markovnikov means that I need to form the most stable carbocation. So in this case, my double bond is going to start and the reaction, and it's going to open, pick up the hydrogen, bromine is going to leave. So now my hydrogen is going to be forced to be on this carbon. Why? Because I need my plus charge to be on this carbon so that it's allylic to this double bond. And this is my target, okay? I always want to form the most stable carbocation. Allylic carbocations are way more stable than a regular tertiary carbocation. If your plus charge is here, then your tertiary carbocation is going to form. Tertiary carbocations are less stable than an allylic carbocation. This is a secondary allylic carbocation. And secondary allylic are more stable than tertiary. Primary allylic are more stable than tertiary. The reason why? Because of resonance in there. So I'm forming my allylic carbocation. I did my, this is on carbon number 1. This is the 1 addition in there. The moment, as I said, the moment you form your allylic carbocation, always do resonance. You cannot break one double bond without breaking the other. So we're going to go ahead and do resonance over here. And once you do resonance, then here you go. That is going to be my double bond, and now my new position of the plus charge is on carbon number 4. Don't forget your substituents. So that is carbon 1, and this is going to be carbon number 4 over here. So now, okay, now before you proceed, and do the next step, which is the bromine addition, we want to go ahead and try the other side over here and see if we can get a better carbocation. So here we got a secondary allylic carbocation and we got a secondary allylic as well. Let's see if the other carbon in there, if we start with it, will give us a better carbocation or a more stable carbocation. Over here, we're going to do exactly the same thing. Go ahead and add the HBr. I'm going to go ahead and number my carbons now. This is going to be carbon 1, this is going to be 2, this is going to be 3, and this is going to be 4. So I'm still going to get the 1,2 addition and the 1,4 addition. The double bond is going to open up, pick up the hydrogen, bromine is going to leave. Now notice here, I need my plus charge to be on this carbon so that it's allylic to the second double bond. So this means that the hydrogen needs to add on carbon number 1. So you're going to end up adding your hydrogen on carbon number 1 in there. And then on carbon number 3, don't forget you have a CH3 in there. Now it is a plus charge. This is going to be allylic, and it is a tertiary allylic. Now you compare the stability of the carbocation that you are forming once you are adding to this carbon versus the carbocation that you formed once you start your reaction from this carbon. This carbocation is slightly more stable than the secondary allylic, so this is the route that we need to continue our reaction with. In this case, you will discard this option here of starting on this carbon, and you will continue your reaction starting with this carbon in there. Let's do resonance and see. So if we go ahead and do resonance, then the resonance is going to be from the double bond towards the positive charge. And in this case, we are going to get another tertiary allylic. So here we're going to end up getting another tertiary allylic. Don't forget, you don't have to show your hydrogen on carbon number 1, but this is going to be carbon 1, carbon 2. I'm just showing it in here just for you to keep a track in there. What did we add? So we are adding the hydrogen on carbon number 1 plus charge on carbon number 2. And then the hydrogen on carbon number 1 and the plus charge is on 4. So bromine is going to be in the solution. So the bromine now is going to come and attack the plus charge. If you are working at a low temperature, this is going to be the 1,2 addition, which is going to be the kinetic product. It's going to be the fast product that forms. Fast product means not a very stable product in there. So the Br minus is going to come and it's going to attack the plus charge in there. Okay. Now, when it attacks the plus charge, since you are creating a chiral center in here, you have 3 different groups and you are adding a 4th one, then in this case, you would need to consider stereochemistry of the reaction and show the bromine attacking either from the top or from the bottom, and change the stereochemistry of the CH3 though. So the bromine, if it attacks from the top, then the CH3 is going to be pushed at the back, and that is going to be your 1,2 addition, okay, plus the other isomer in there where the bromine can attack from the back and push the CH3 to the front. Here you go. So these two, and don't forget your double bond in there. These two over here are going to be the 1,2 addition. These are the kinetic products, and they're going to favor the low temperature. These are considered to be pair of enantiomers in there. This is the only chiral center in here. And these chiral centers are mirror images to each other. So you are getting a pair of enantiomers for the 1,2 addition. Now for the 1,4 addition, go ahead and add a bromine in there. This is the Br negative. This is your nucleophile. So the nucleophile is going to come and look for the electrophile and attack the electrophile. And again, on this carbon over here, I have a potential chiral center. The groups are different. It's a CH3, it's a CH2, and it's a CH. So the groups are different in there. And you're introducing a bromine. This is a fourth one. So the bromine now has the possibility to attack from either sides. Please remember that you need to have a double bond between carbons 2 and 3 for the 1,4 addition, and a double bond between carbons 3 and 4 for the 1,2 addition. Don't forget this double bond. So if the CH3 or if the bromine is attacking from the top, then the CH3 is going to be pushed at the back. And same thing over here. Don't forget the CH3. And then if the bromine attacks from the back, then the CH3 is going to be pushed to the front in there. And again, you are going to end up getting a pair of enantiomers. This is the 1,4 addition. On carbon 1, you added your hydrogen. And on carbon number 4, you added your bromine. Okay? And this 1,4 addition, this is a thermodynamic product, and that product is going to happen at a high temperature.